I will continue from where I left off earlier. I was trying to show you that for you to start making a layout of an equipment, you probably have to do what we do in most of the other two conditions. In the case of design, and when you want to patent some of your whatever creations, what do? Is you check the usual need analysis and all that, and then since we are down in the embodiment design phase of it, one of the first thing when we do the embodiment design is also check for prior art. I do not know, kindly put up with my accented language. Prior art refers to saying what is already existing. This is part of the intellectual property, this thing. So, this is not about copying. Copying is something else. You can always license things and all. So, one of the thing in prior art is you go and check on the existing solutions which is already there. So, if you can adopt some of the techniques which have a what do you call validity and they have been around for quite some time, nothing like it. Equivalent of it in the academic field are all the published articles. In both the cases, the most important thing is we acknowledge the what do you call the source and so on. So, allow me to start with one of the things which is shown here. This is a very what do you call large thing saying investigation of heat transfer through embossed fin and so on. There is an abstract, a reasonable thing. I would like to acknowledge the people from Dehradun 2014 and so on. One of the starting points which you need to do is commonly used orientations of a straight fin natural convection heat sinks are vertical base plate with vertical fin channels, horizontal base plate with fins facing up, vertical base plate with horizontal fin channels as shown. So, a vertical base plate with a vertical fin channel delivers the best performance for natural cooling. So, I would like to just take you to the figure because it is convenient. I think it looks almost intuitive. Vertical base plate, best configuration, vertical base plate, horizontal fin channels not the best, but better than a flat wall. Horizontal base plate faces up as good as the vertical and vertical configuration. So, I mean I will allow me not to comment on it. Now, working towards it, I will just minimize this, I will go back with something which is there in the background here. Then there are several industry catalogs. Same thing repeated again, which I have shown you earlier, except that this is from a commercial source, that is somebody who supplies all these things. So, they have written a little about what is what you call convection cooling and so on. This is what I have kept on repeating to you earlier. Due to the relatively low airflow generated by natural convection, the fin pattern will need to be very sparse to provide optimal performance. A dense fin pattern will generate too much. It is not exactly true, it is just the slightly what you call, there is an optimum thing which is there. So, it is obvious this figure just shows you how the hot air comes and all that, heat is trapped between fins and so on. So, LPD series and so on. Now, this comes to the other way of looking at these things. So, we have vertical and horizontal. So, 1, 2, 3. So, they have given here based on our testing, if the heat sink is the thermal performance is 25% worse than in the other figure, meaning if you orientate something vertically, meaning the fins are like this. So, I have a thing here, I will just show it to you. Oh, I have a sample here. So, obviously there are several ways, one way is making it like this, one way is making like this, and then one way is making like, it does not really matter which way it is. So, I think it is very intuitive and correct saying no, this is best, this is not so great. If it were to be vertical like this, you need spacing here, you understand, no? You more like a pin fin configuration should be there, then the configurations will work. Now, we come to some things like this which are on both the directions. So, if you mount a power dissipating component here, it does not look intuitive that this the one in the bottom, I doubt whether it actually can do any good at all. You have seen this, no? So, obviously such thing there is only one way to mount, vertical, and in vertical again we need to provide some sort of a what you call cover over this, and then after that neatly it just sits there like that. Now, when we keep it in horizontal, now we know that this is obviously not at all designed for such a condition. Yes, provided you give relief, best keep it like this, not a proper way of doing it, which in this case, can you put this, sir? So, in this case all the other things are, we can put it like this, we can put it like this, or we can put it like this. Now comes the thing is, how do we integrate these things and what you do, and also a lot of stuff about power dissipation and so on under natural convection. So many of these correlations have been given here. If you go to several of these what do you call sources and all that, no, enough information is available. Now, I thought I will start here with, sir, if you can kindly put the, I will start with having estimated what is the loss in your equipment, meaning if it is a maybe a 10 kilowatt device, and then you expect that steady state losses at the appropriate loads which we know. Partial load, it is very inefficient, overload is inefficient, at correct one load the efficiency will the optimal, or the probably the best efficiency you can get is about 90%. So, 10% losses will be there. Now, based on this 10% losses, we can choose a heat sink as a starting point, saying when the heat sink is kept in the fins vertical position and you select something from the catalog, and then you see here I wanted to jump from here to the way how do you create this heat sink from the catalog, and then how do you try to use it in your equipment. So, I randomly picked up something which is a profile which is 174 millimeters wide and 28 millimeters high. So, if you see here, most likely from here to here this dimension is about, say if you remove this 4 from this now, typically about an inch, which is about 25 mm deep, and then this 4 mm typically corresponds to a little more than a 1/8 of an inch. Okay. Then 175, I think if you know the what you call equivalent, it should be about 7 inches. So, starting this point, I thought we now need to try to create the 3D model in this. I am using what do you call free or trial version of a what do you call CAD, which you can, we of course have the licenses for this. The another place which I work, which I teach this, has the licenses. This has been taken from here. So, if you see this, this is typically any package from any source you can use, there is no problem. And I would prefer something which is relatively easy to work. So, one of these things is here we have, for example, I have started with this beautiful background bitmap which is already placed there for me to trace. So, those numbers that 174, 4 and 28 is exactly what we have had there, and then over it I tried to trace and then I tried to make something which a little, what do you call, just to show that how well it is, how well it is not. I will just move it out. Can you see it is not actually a very good not a very, what do you call, very accurate representation, but good enough for us. Main thing is everything has been rounded off. One of them is the width of the fence, another is the thing, but total number is maintained, dimension 28 also is maintained, and when if I go put it back where it belongs, you see here it is almost, it covers the that thing. So, I have now a starting point for a heat sink, and then I will now hide that bitmap. See, I have this beautiful heat sink profile which is there. Why I am doing this is, now if you go into the 3D version of it, see, I have this beautiful heat sink which is extruded in the Z direction. Why I need to show you this is, now this is probably our starting point of various products which we want to do. Once in your what do you call career, whether you are a just packaging person, electrical person, or you are a manufacturing person, if you create the drawings for these profiles, you can use them everywhere else, because typically if you notice the fin spacing, fin proportions are all about the same, and things have been built on this. Now, just for this thing of it, I will start with a what do you call this profile. Imagine now I need to make an equipment which needs some what do you call cooling or anything. Top view looks like this is the front view, then this is the side view, and we have various things like. Now, that is a matter of my placing the heat sinks symmetrically on see, my starting is slowly getting ready. So, I have two heat sinks which are in the vertical direction, and then if I choose the appropriate method of demonstration, you see I have a beautiful starting point for all these things. Two heat sinks in the vertical direction, and then the dimensions are probably determined by the other proportions. If it is a rack mounted equipment, usually the front is a 19-inch panel. Inside, what goes inside is, if you take 426 as the width, 19 inch as the width, usually if you leave 20 for the flanges, remaining happily goes inside the rack. These standards you need to verify, you should not take it from me now. So, if you verify the standards, you will know the width. Similarly, if you take the height, it goes in terms of U's. 1 U is 44.45 blah blah blah, and then generally 3 U. Typically 3 U rack will be 132.5, and this is a good starting point for a rack with heat sinks in the vertical direction on the face back things. Now, while this is one of the what do you call conditions, it is not the only way you can do it. It is very much possible for me I will try to go out. I have a single what do you call heat sink at this at the back. It is possible for me now to make various types of, I will just try to see what best I can do here. Now, I will start with another what do you call see here I have something which forms the base of the unit. So, all I need to do is, now I can just do the extrusion as I have done before. I have my enclosure getting ready. Very interesting thing, no? What I have started with is just a profile of the heat sink. Now, two variants I have shown. One of them is saying the heat sinks can be on the either of the sides, left and right. So, at the back we have this extrusion which is going up. Now, you need to place the various controls on the front panel and start working on it, which is a relatively easy way of doing it. Again, the starting point is that you need to trace or create a library, and generally within a particular what do you call area of work, or the area in which the enterprise or the design house is trying to work, will be trying to deal with certain sizes, certain things and all that. I showed you yesterday what is called the 1/8 brick, half brick, quarter brick and all, which comes from probably naval and aircraft power supply. So, if you take the brick power supply, it has certain proportions and you have orientations of vertical and horizontal. Here I have shown you what is obviously really what you call nice way of seeing these things. Seen this, no? So, I have got a got a device which has the heat sinks at the back. Now, this ought to be the starting point and not there is no equation which directly gives you how to do it. Everything depends on your product design. So, in this case you can have them on the side, or you can have this, any other way is possible. Of course, other way is possible, nothing restricts us saying you need to keep it at the back. Sometimes it happens, as in the case of equipment which are directly mounted in a rack and you have no access to the remaining parts of the rack. So, even heat sinks come out onto the front of the rack. I am sure if you are a professional you will probably agree. Now at this point it is very much possible for me to start working again in this. Okay. See, what I do is now I will try to make something and remove you see have a neat little front panel where I have made a little bit of space so that my it could be now we have a full flat what do you call capacitive or resistive display. Alternatively earlier you used to have various types of knobs. This is typically how equipment at the turn of what you call just about just before the Second World War were all built. Now we play around, not play around, I am sorry, now we try to adjust for total amount of space available and whether the spacing is sufficient or anything, but the starting point is the profile which I had started there. Now you see here very neatly I have everything almost worked up for me. And I can continue to these edges look a little sharp, which I do not need such sharpness. So, I will see if I can cure the unwanted sharpness problem. I will try to one more time I will try to create I just wanted to chamfer it. There are so many other ways of doing it is there, I am sure now. If you are one of the persons who enjoy this sort of what you call solid modeling methods, I do the same object which I have done earlier. See, now I have got a much more presentable and smoother way of easier way of managing with my profile which I have started. So, this can continue without the any this thing. Otherwise, you also have solid things like if you go to the solid editing, in solid we also have these things like what do you call filleting the edge and so on, fillet edge, and then I make a what do you call 6 mm fillet. See there, it has become rounded there because what I expect is when you are trying to operate a control, most likely we would like to have a smooth rounded edge and not a chamfered edge. So, now I can continue this filleting with all the surfaces that are present here, saying now if I to take it out further, yes, in this I have got a nice partly protected enclosure which is not harsh on the operator, and from this point is when where your analysis need to take place. Now you see suddenly what we know about this height of this heat sink, and then the depth of these fins, and then the spacing and all that is probably valid only for this section of the heat sink. And if you now go to the manufacturer's catalog, the remaining thing, it is for you to make the nearest approximation. That is probably total length available for you is ml about half, and that is unlikely that we have used this back surface. The surface will not be used for mounting anything, that will be a nuisance, no. So, it is likely that this whole thing is actually can be an opening. So, we have, I will again go to the front and then see whether I can create a proper this looks like a better option. So, behind that we can continue to have whatever control or display systems we have, but the heat dissipating part is only the little bit of heat sinks in the top of it and the heat sink which is there on the side of it, but on the remember is on the front surface. Same thing is equally valid when it comes to the rear of the equipment. Now, if you go back and check some of these audio equipment or even these routers and all, you will notice that this is exactly what they would have done, especially if you are trying to mill something out of an existing solid, or some of these new plastics, they tolerate higher temperature. So, sometimes you find that the panel is plastic and inside there is a small opening, probably the heat sink fins project out of it, or in the case of things like of our what do you call power supplies and those things, there is a heat spreader and this bridge which directly touches the surface of the cover. So, when it touches surface of the cover and things come out, you will be able to clearly see that heat is allowed to dissipate through the otherwise inert plastic case, which is not thermally conductive. So, this is only one instance of my telling you. So, what I will do at this point, I will just give it a save and then open the earlier drawing which I have started with. See this, I have shown you that when we can keep them on the side or we can keep them on the back and so on, and our one proportion. Now, let me go to another slightly different way of doing this. What I will do in this case is, because of various of my necessity of this demonstration, I will try to take a heat sink which is slightly smaller. In this, I will remove these two mounting plates here, probably I will remove this also. And then I will just leave a couple of fins and then see whether it is possible for me to make something which is equally interesting. You see where I have started. Now, one more time I will try to make the extend curve command and try to trim this object. And attach all of them together. See here I have a beautiful profile which about looks like this. I will just switch off this grid, which is a little distracting. Now, this being on the top surface, I will try to do something else. What is done here is, this is now starting of a different way of making it. As before, what I will try to do now is saying, see whether I can build an equipment which is see here, if you see, this is where we are talking about. One more time now, I will try to make a solid, a box corner to corner. See, quite good. It looks a little like the vertical mounted inverters which I have shown you, that solar inverters. So, we have here sides of it which form a vertical heat sink, and they are running on the side. So, the back can be mounted directly, and the front you can have a front panel as you like. Now, several options are there. One of them is I can try to cover the whole thing in the front with a equally interesting thing, which I will try to see whether I can make something here. See here, I have a small section which I can now try to do the various trimming operations and so on. Sorry. See, I have got a cute, neat front panel slowly coming up. I will try to join this into a single what do you call polyline. Now mirror it like before. See, I have got what is obviously a nice curve here, and if I see where it is, this curve is sitting on top of it here. Can you see here? So, it is for me, it is very much possible for me now to try to extrude the curve. See, slowly my equipment is getting ready. So, one of the things you will notice is I have a front panel here. I can do various operations with the front panel, including see here. See, beautiful, nice equipment is almost ready, but if you see the starting point was the same profile which I had taken off from one of the manufacturer's catalog, which is probably once again based on prior art, saying what the other people have been using. Now, in this equipment I have the what do you call left side and the right side what do you call access to the various devices. Then I have a front panel here, and still I have the back panel which is open there. Now, it is for me to once again not decide whether I cover the back panel also with heat sinks, or one more thing which I thought which is not so great is since the top surface is still available, can we do something with it? Other options are also possible. For example, this heat sink can be kept back to back, and then we can provide a small fan, and then what you call, make sure that the, you have seen this, I have a heat sink here. What I will do is, I will take the heat sink here, I will take this heat sink there, move them both, it will close. Temporarily I will delete the, you have seen here, now I have got a configuration where the heat dissipators are all facing inside and outside there is nothing, and then it is very easy for me to provide a small fan at the bottom or on the top and use forced cooling. Advantage of this is, in the smaller size density, tremendous amount of what you call heat of the order of up to 4 times can be accommodated, and probably we can have 2 channels of it, like one channel is here, same I can now use this for have one more of it here. Which is probably one of the reasons I had started with. See this, I have got a nice tolerable project coming up. I have now a device which can probably have 2 small fans at the bottom in the blow position, or 2 exhaust position in 2 fans on top, and this whole thing forms a module. That is what I was talking to you about. This is probably exactly how these things have been generated. The common thing is probably a profile like this which has been tried and tested, then somebody has been what you call experimenting on this various profile, and in the normal condition, if you were to make them in the vertical what you call orientation and then adjust the total length and the power dissipation. Another very critical component is there, especially regarding convection and from the device. These heat sinks have one peculiar what you call issues which we talk about. If the heat sink is cold, meaning the temperature is low, final steady state temperature, rate of heat transfer from the device or inside will be highest, maximum temperature differential will be there. However, if this is low, it cannot really transfer any heat to the ambient, looks a little anomaly. Now, the other option is, if this is high, it can transfer the heat directly to the ambient very well, but inside you will have a problem of not able to take. So, more by experimentation, a little bit of thing by hand calculation, we need to find out which is good. So, some people have suggested approximately half. Imagine your inside ambient is likely to be around 80 degrees, all the device and all, and ambient outside ambient is likely to be 40. So, if you are to maintain it 60 to 40, you still have a differential. Well, inside 80 to 60 also you have a differential. Probably one of the reasons why there are fins on the inside also. Got it, no? So, these fins transfer heat from the inside the equipment, and this forms the enclosure. So, 2 of them back to back form the enclosure. You have things recirculation, and inside you do not need a fan directly here. All you need is something which recirculates the air and then removes the hot spot, and outside conducts the heat away to the atmosphere, and inside things are equalized, and then things look very neat and very clean inside. So, the starting point is we can always start with things like this. Oh, I am not able to enlarge it to full, but we have a beautiful rendering frame. So, several of these things you will notice are this way of trying all possible configurations. So, I have shown you something, and this point now I will try to go back and try to undo, remove one of these things which I feel now is not very useful for me. See this is where we have started. Okay. Now, I leave, why do I leave? I mean, there is no necessity for me to leave it like this, because top surface is still available. So, why not provide one more of these devices directly on top here? Now, if you come back here, you will notice I have an equally interesting configuration of fins being there on the top of the equipment also. So, at this point, depending on what I have told you earlier, it is possible for us to now provide some what do you call slits and all that, and make an interesting industrial design, or very interesting what do you call prospect of having an equipment in which the top and the side surfaces are also used. And at this point you can start doing the actual calculations about what will be the net result of the this thing, what will be the thermal resistance of it, and so on. Next time if you look around, every configuration I have spoken about probably already exists. Okay. While it is novel and probably you cannot patent it, you can what do you call address your problem and then try to solve these problems like this. So, this is I have told you about something is on this side, then I told you something about the front with the clearance and something about this, and the very starting point is saying we can even have this fins directly at the back, which is what a lot of this electronic cooling at the equipment level is about. And the depending on the volume that you make, for example, on these solar devices and all that, this configuration, in the earlier configuration we have made a solar pump. Somehow I am not able to get the picture of it, because this what you call drive for a solar pump is to be used in the field where you do not want distracting what you call things like voltage, current, and whether it is following the maximum power point, season and all that is not interesting. That had only one switch in the front. You press the switch, if everything is fine, the motor starts and the pumping starts. If it does not start, you have an error saying probably there is not enough sun or anything, just one indication saying wait for the sun. And then the user just needs to wait and then press one more button and it starts and pumps, and MPPT is built into it. Maximum power point is about tracking the impedance, not about tracking the position of the sun. Tracking the position of the sun is what you call somewhat wasteful, and only in very extreme I mean special conditions probably that is need to be done. Otherwise simple clockwork will work, and probably 3 positions is enough, something start of the day, midday, and then what do you call end of the day, probably the 3 positions, and then a very tiny very low power mechanism which orients it like this. That coupled with my design here is probably how in reality projects are made. And then yesterday I showed you one picture of a data acquisition system. That other modules which we are talking about also had a similar look or a style, which all had this front panel like this, and then there were these heat sinks, whether hidden at the back or anything on the side, and at the bottom, if you recollect, there were two connectors, and the connectors have been made such that they cannot be confused with each other. So, the input to this equipment is through a cable which has sockets at the end. Sockets generally that comes from the solar this thing. Sockets is where always you take the power out, and they connect to plugs in this unit. Other side, where it goes to the pump, sockets are mounted on it. Again one more small, probably it was a 3-pin or 4-pin device which will go to the pump. Now, moment you have these sockets and things like this, which are also typically mill grade, they can tolerate much higher temperature. So, you can afford to have an enclosure like this, probably whole thing made out of an aluminum, die cast aluminum, and you just need to, there is a cavity like thing with milling, milled fins everywhere, open the cavity, mount everything, close it. So, it has the second benefit of being fully waterproof, and if the connectors have the correct grade, making IP 667 is not an impossible task, and instantly these devices will help us in realizing these things. So, I think that will be enough for today. I will stop. I will try to continue little more about these things in the subsequent lectures. So, thank you.